Hi everybody. This is Alex Lannan from Dynamic Devices, and I just wanted to talk to you today about what we've been doing with the Digital Catapult here in the UK as a part of one of the Technology Access Programs, or TAPS, for the past few months. So this is really exciting stuff. We began to work with them and with Cambridge University and ARM on a project that's been ongoing for quite some time now, which is the CHERI architecture. And there is a Morello board, which is a sort of physical motherboard that has been put together by ARM, implementing this new to us CHERI architecture. So what I want to do is have a little chat with you about what CHERI is, why it's exciting, and then move on to talk a little bit about what we've been doing and where we got to, who we've been working with, and some next steps. So, okay, fantastic. Now, CHERI is the Capability Hardware Enhanced RISC instruction set, which is all, wow, what does that mean? Well, try and think about it like this. So, back in the mists of time, we began with 8-bit, or even before 8-bit microcomputers, and you could write some code on these things, the code would run, and you might do some memory accesses. And one of the big problems we had was that if you could access the entire memory address space, so your program and any other programs that might be around and about, you could corrupt other bits of memory if you got things wrong. And that was a real problem, and it made it really difficult to write resilient software, particularly in the embedded space where I come from. So, time progressed and chip architectures improved, and we had these things coming along called virtual memory managers. And what you can sort of think of that as is, you've got different processes running in your multitasking computer, your application here, your application there, and each one of them has its own virtual memory map that is underlined with the raw physical memory. And so a particular application can only access its own memory. So if I'm doing things in my application and it goes wrong, worst thing I can do is take my application down. I can't actually take down all the other applications, or at least that's the thinking. So that helped, made software more reliable, which is a good thing. Now then we move into the security space and the bad people. And what can happen is, they're looking for ways to exploit limitations and errors and problems with the code that we write. So if they can get into a system and exploit those issues, they can then maybe get themselves more access privileges. They can get to do stuff that we don't really want them to be doing. And particularly nowadays that everything's internet connected, if I've got a box and it's sitting on an internet connection and anybody can get into this thing, and I've got it all locked down and secured, but if they can find a way to sort of, get through some problem that we've got, who knows what they might be able to do. And this is a real risk. You probably, you see constantly that we have these kinds of problems occurring. So for example, if I'm running a web server and the web server has some bugs and somebody figures out how to use those bugs to get into the operating system and escalate their privileges, they can do really, really bad things. How can we try to mitigate this set of threats? Well, this is what CHERI is all about. So one of the ways that is really, really common for somebody to try to exploit a piece of software is to do with something called buffer overflows. And what you might think of is, if I've got a block of memory and I'm using that for some purposes, I've got some strings in some values, is what it might be, and I grab that memory within my program, and then, really, if you think about how a computer works, that bit of memory that I'm using is just part of the overall memory that's sitting there. And there'll be sort of other stuff before that block of memory and after that block of memory, which is memory being used for other purposes. So what people try to do is they say, well, look, if I can put some information into this block of memory and then I can kind of overwrite past the end of it, I can probably put information where it's not supposed to be. And if I'm really clever about that, then the information I can sort of put where it's not supposed to be, I can use to control the execution of the program in the way I want it to work and make it do things that it was not designed to do and shouldn't be doing. And so these are sort of generically termed buffer overflow exploits. And there are similar things. That's a big class of exploitation problems. So that's a real problem. Even with current memory systems, current CPU architectures, x86, ARM, whatever it might be, within my program, I'm allocating a block of memory for this string, and it doesn't know underneath, in the hardware, that somebody shouldn't write across the end, off the end of that buffer. Now I probably should do stuff in my software to kind of prevent that, pass inputs, check lengths, but we're all human and we make mistakes, and you only have to make this mistake once in a lot of code, and for somebody to find it, you got a problem. Now there are lots of projects out there to try to mitigate this. You got Rust, you got Go, you've got programming language frameworks which are designed to protect you against these kinds of problems, and they're great. This is not to say that there's anything wrong with that. That's a great thing, but this is another approach, which is to actually modify the hardware in the chip so that when I say, hey, I'd like this block of memory and I'd like to do something with it, the hardware knows in a pretty fine-grained, granular kind of way that I've grabbed that and I'm going to do something with it. And then if somebody tries to write past the end of it, the hardware says, you can't do that. That's naughty. That's not going to happen. So it protects me as a programmer, as a coder, against the kind of mistakes that we all make. And that's great. So, the more that we can do to have safe environments to write code in, particularly on internet-connected devices, the better for everybody. So that's what CHERI's about. Now, I'm just a programmer, so, if you want to look at the real hardcore ins and outs of how this architecture has come about over a very long time and the project that has been worked upon here, you can have a look at the University of Cambridge Department of Computer Science and Technology. You can see on the webpage here, and they talk about what CHERI is all about and the project and where it's come from and who they work with and examples of what they have been doing with it. In particular, if I go over to look at the Morello board, as I said at the beginning, this is this sort of physical main board produced by ARM. We have one here. We're very, very lucky to be able to work with it as a part of this Digital Security by Design Technology Access Program. Absolutely fantastic. And so we're sort of running code on this CHERI architecture and testing out what it can protect against and what it does and how well it works. Now, they have a software stack, as a number of software stacks that they've been working on for quite some time, which are brilliant. And you can have a look here at what they can provide, what they do provide rather. And in particular, again, you can look at CHERI BSD. And a lot of work has gone on with the team over there supporting a buildable, runnable BSD operating system environment that supports or runs on top of the CHERI architecture. And they've been porting lots and lots of software packages in, and that's probably a great place to go and start to look at all of this stuff. In addition, they've got some Android support, and you look at that too. Go and have a look at the website here. This is the place to go. Now, for me, my background is with embedded systems. I do a lot of work, have done with Yocto, with Open Embedded, which is essentially a tool chain for building up embedded Linux distributions. I did a lot of commercial work with that and tried to contribute to that. And so it struck me that it would be really interesting if we could see how far we could get putting Yocto onto CHERI, beginning in a small way to sort of see how we could protect the applications that were running on hardware, target hardware, which in future can support this CHERI architecture. Yocto is designed to support multiple different target boards, multiple different chip architectures, so it's a really good fit. And that indeed was where we began with this project. That's what we started looking at. We spent some time coming up the curve with all the wonderful stuff that CHERI can offer to us. And as a part of that discovery phase, we found that there are some people who have already been working on adding Yocto support for CHERI. And these are great guys. These are some people called The Good Penguin is the business. So props and a shout out to the head guy there, which is Andrew Murray, and one of the developers I've been working closely with, Powell. Now, if you go to their GitHub repo here, they have the beginnings of a buildable Yocto environment that we can deploy onto our Morello board and start experimenting with using the CHERI instruction set architecture to protect against exploitation and against security failures. So what I'm going to do now is to move on to that and show you what we can do with this great work of theirs. So if I move over to a couple of terminals that I've got opened up here, what you can see is that I've got a couple of minicoms, a couple of serial terminals up at the top, and then I've got a shell that we'll look at in a bit down at the bottom. And what I can also show you, if I can bring this up, is that I've got a capture of the output of the actual Morello box down at the bottom right there that you can see. So how is all this wired up? Well, we've got the physical box that I've got here. That's connected through a USB connection to my system, and that is enumerating up as a number of different serial ports which output different kinds of information. Two of those we care about are, there's a kind of an underlying command shell that we can use to manage this Morello system, and then there's the kind of more usual sort of boot shell that you would sort of see when your system comes up. And then down at the bottom right, you won't be able to see very much with this, but this is actually a capture of the HDMI output of the box. So that's what you would see on an actual display. Now, if I essentially go in and reset this this board, we see it come up, reboot, and it takes a little while for it to get itself set up. It's loading in. I think it's FPGA based actually, so it's sort of loading in the CHERI architecture instruction set, the implementation that we're currently using as it goes. So it's doing that now, and if we just hold on a little bit, we will start to see our more sort of standard boot shell coming up on the right hand side. So bear with. Okay, so that's starting to come up, and we're going to have the bootloader coming up any time now. So you can see the HDMI output in the bottom right as it starts. And there we go. So we kind of got the same thing going on here. We've got a serial output on the top right, which is equivalent to what we've got going on the bottom right. Now by default, when we got going with this, we installed CHERI BSD, which is a great place to start. So maybe that's one thing that you could be doing. You could be looking at how to build up and install CHERI BSD on these kinds of platforms. But what we're particularly interested in is Yocto. So I just want to show you what we've got with the great work of the people over at The Good Penguin, which has enabled us to effectively put a bootable build of Yocto on a USB stick, which is sitting connected to the Morello board. And I'm going to try, instead of booting into CHERI BSD as default, I'm going to boot into Yocto. And then we'll have a quick look at that. We'll see that booting up to a command line. You'll see all the usual Yocto stuff. And then I'm going to take a step back after that, and I'm just going to show you how we stepped through getting that code from the Good Penguin repository and building it up locally and deploying that onto the USB stick. So if I just need to jump in fairly quickly here to try to break out of the automated bootloader boot. And there we go, and we're now into sort of the equivalent of what you might think of as a basic BIOS. And I can go down through that into the boot manager. And within the boot manager, I can go down and I can go to the mass storage device. I can't actually see it being selected here, so I'm just going to have to hope for the best, I guess. And so now we're going to select the boot from USB, which I do here. And you can see, rather amazingly, what that's done is it's read off the bootloader from the USB stick, and it's giving this the option to boot up this BusyBox Morello platform image that we've built. So if I select that, you can see the usual, the good stuff. We've got a Linux kernel that's running. It takes us down to a command line. It's a standard that was based on the standard Pocky reference distribution. And we've got a login prompt, which we can log in at, and we've got our file system, and we can do all the usual stuff, looking at what is going on that system, how it's all running. And we can then, one of the initial applications that we've got here as an example application of how to exercise the CHERI capabilities to protect us against invalid or incorrect or unwanted accesses to memory that shouldn't be accessed. We can run this application. It's got a couple of initial basic tests we can run, and we can run, for example, an out of bounds memory access, which runs, and then there is a signal being caught when that errors by CHERI coming back to a signal handler for us and telling us, no, you're not allowed to do that. So that's a really basic example of how we can begin to build Yocto support to protect us using this CHERI architecture. And what I'm now going to do is to move on and show you how we build this up and how we get this onto boot on the Morello platform. So let's just get rid of this screen output, because we, there's not a lot that it's telling us at the moment. It's not particularly helpful. And if we go back to have a quick look at the web browser, there's a couple of things here. So the code base you want to be looking at is at the Good Penguin Meta Morello layer. That's where Powell is building all of this up. It's great work. Now, I won't take you through all the ins and outs of building Yocto. I mean, there's a lot of reference material out there that you can use. What I would say is that my preferred way to build Yocto today is within Docker containers. I find that really useful, and it's because I've got my host system, my real system, if you like, but you need a set, as with all software, you need a set of dependencies and installations and versions of things, and it's all going to be right. You've got to have that stuff there. Yocto tries to insulate you against that, but you still do need a set of stuff installed on your host. And like any developer, my host systems change around all over the place as I'm fiddling with stuff. So what I like to do is to have a kind of a sandbox as a known host environment, which Yocto is going to build within, and it's always going to be the same, and it's never going to change whatever I happen to be fiddling about with outside of that space. So as ever, open source, ain't it grand? There's some useful stuff that you can leverage to build a Docker container with all the right dependencies that you're going to need for Yocto. There's something called IMX Docker, which is not mine. It's something I use. I have a fork here on Dynamic Devices because I've had to add in some additional dependencies for the things that I do. I would say, go and take a look at that. That might help you. You can use one of these Docker files to build up an image with all the dependencies that you might need. See a few bits and bobs that I needed to add in to get Meta Morello building. And then you can use that, and there's a kind of standard example run file which will basically enter into that container that you've got there and allow you to start building up Yocto. So that's what I do. Take a look at that. If I go back over to the program workspace, you see in here I have this run docker command, and essentially what that's going to do is just try and start up an IMX Yocto container that I've built. You can push this up to the Docker hub. So if you want to, you can just pull down dynamic devices imx.yocto if you don't want to go through the pain of building the thing yourself. And if I then run that, get a command line, doesn't look all that different, does it? But what I've got here is I'm now within that Docker container, so everything that's going to build will be building with those known install tools and libraries and so on and so forth. So that's my space here. Now what's really quite important to understand if you're going to go and do this is that the way we run this Docker container, we break out a couple of mount points. That's what these two lines are doing. Because if you run inside a Docker container, when you leave that container and tear it down, everything that you did inside that container disappears for good reasons. So every time you restart it, it's always going to be the same. It's always going to be in a known state. Now that's no good for us because we want to build there's a huge amount of building that needs to go on with Yocto, and we don't want to have to do that every time. So what we do is we kind of break out of the container so that all of these build artifacts and the outputs of what we're doing are going to be stored in a tree, a file system tree on the host operating system. So I bring up my container, do all the building, that all gets stored nice, neat and safe, take down the container, and I've still got everything, and I can build it up again and I can continue from where I left off. And that's really important because depending on your hardware system, you know, Yocto can take many hours to do its build. It's doing a lot of work. So let's go back into the Docker container. And what I've got is I've made a git clone of the Meta Morello layer, which you can see here. And that's pulled down from the Good Penguin. Now we go and have a quick look at the instructions on how to run this up. There are some mailing lists that are probably worth having a look at as a first point of call into here. Take a look at this mailing list here, which is where everybody's chatting about Yocto with CHERI. And the ARM folks are in there. They're doing some great things. Pavel is contributing through this list. And one of the things that was suggested was that they like this CAS build system, which I confess I've not really used myself before. Now, as with Android, a lot of people, myself included, have used a repo tool that pulls down a load of dependencies and gets you going to be able to build Yocto images. And it's okay, but for me and seemingly others, it doesn't quite do everything I'd like it to do and automate the things I'd like it to automate. Whereas apparently there are some other solutions out there, and one of these is CAS, and you can basically do that thing, like with CI, where you can script up CAS to grab everything, get it all set up, and go and do the build. So the way that we do this, building images, is CAS build with that script from the repository. And if we go back to our container and we try to do our CAS build, there we go. And so that's doing a bunch of things. It's pulling down the dependencies it needs. It's starting off the Yocto build here, where with the Kirkstone releases you can see blah, blah, blah. Now, so as not to keep you here for many, many hours, in finest traditions, here's one I have built earlier. So effectively, it knows that it's already built everything up and it's not going to try and do that again. And if I look in the build directory, there's two trees I'm interested in here. There's a TMP BSP and a TMP Linux. Again, going back to the instructions, what we need to do is we need to take an output image from our TMP BSP tree, and we need to program that onto an internal SD card in our Morello board, which I'm going to show you in a sec. And then there's another, and that's kind of like the base support for all of this for the BSP. This is external to what we're talking about with Yocto. This is the CHERI magic. And then we've got a separate image, which is our more what we would expect with our Yocto image, which is built in Temp Linux, this Morello Linux image that we're looking at there, and we can put that onto the USB stick. So first things first, if I go back over to my programming windows here, when I connected up the Morello board with USB, and I was talking to you about it enumerating a number of different serial ports, well, it's also got some, it enumerates up as an SD card. So if I have a little look and see where that is, what I'm just going to do is reconnect, because I think my USB hub has gone down. So if you look here, you can see that I've got an SDB device. Now that is the SD card in the Morello system enumerated up over USB, and if I take a little look at what's going on there, that's mounted. So if I look in you see some software files, and essentially what you need to do is to overwrite those with the files that are in the image, so, or in the temp BSP image. So if I go into my temp BSP, follows a pretty standard Yocto file system hierarchy. So if we're going to deploy images, Morello BSP, in here you can see there's a board firmware SD image.image. And then what you need to do is you need to take that and you need to DD that onto our dev, whatever it might be, in this case SDB, and that will write those files onto the SD card in the Morello board for you. The next time you reboot the Morello board, it will pick up those files and it will internally reprogram what it needs to reprogram. So that's the first step. I've already done that, so I won't go through that again. Now, the next thing that you need to do is to go into Temp Linux, same setup, so deploy images, Morello Linux ulibc, and in here, if you build Yocto, you'll recognize all of this stuff. We've got an image file, Morello Linux image c64glibc.image, and what you then need to do is to take that, and similarly, you need to sudo dd if equals that image, of onto whatever your USB stick is that you're using. So insert a USB stick. It's not all that big. And then dd that onto your USB stick, put that into the back of your system, and off you go. And then what will happen is, as you boot that up, I showed you, break into the bootloader, you can load from USB stick, and you will then have a wonderful little Yocto root file system booted up to play with and to do testing with. How fantastic is that? So the next steps, well, the next steps are to try to enhance the recipes that we have within Yocto with some CHERI capable recipes. And particularly I'm interested in looking at web-facing applications and how we protect those. So I'm quite interested in looking at whether we can find some Apache Nginx recipes, move them into this Meta Morello layer, or reference through the Meta Morello layer to cherify them up and prove out that CHERI is in fact protecting this system against these kinds of attacks that can take place. So quite excited about that. Those are next steps. Looking forward to working with the Good Penguin to contribute some of this back towards the great work that they've been doing. In addition, huge amounts of work has been done by the people behind CHERI BSD and with the Android team. So I'm really keen to engage there and to leverage that time and effort that they put in and see if we can look at some of the sort of CHERI BSD packages and work out how to bring some of those in easily into this Yocto ecosystem. Ideally, I mean, if there's a way to automate that, that would be fantastic, wouldn't it? So hopefully that's been interesting. That's where we have gotten to today, and I look forward to updating you with progress as we near the end of the project in the next few months.